this is the beginning of the homework help videos for Chapter 7 for statistics. When a measurement is made in statistics, the question is, how good is that measurement? Does it reflect the entire population? Because of course you're using a sample, since the population is too big to measure. You want to know how good is that measurement. Instead of saying it's 95% good or 85% good or something like that, statistics, that measurement is used as the center of an interval. That's called the confidence interval. And the confidence level is how confident you are, like 95% confident, that the true value is within that interval. You've probably seen measurements like that. There'll be a dot, then there'll be a line like this. Okay, and this would be the measurement value, say 10, and this might go from, say, 10.5 down to 9.5. And then the statement is that with 95 or some sort of percent confidence, the actual value lies in this interval between 9.5 and 10.5, where 10 is the actual value that you measured. This whole idea will become clear throughout this chapter. But the basis of the whole idea is the central limit theorem, and that's why the first part of the homework starts with the central limit theorem. This theorem was introduced in the last chapter but not really used. It's used, though, in this chapter. So the first question is, what is the subject matter, or what are the data values that make up the central limit theorem? The scenario behind the central limit theorem is that you have some population, and from that population you pick samples, like samples of 10, I don't know, whatever you're trying to measure, 10 logs. And then you might go and pick another 10 logs on another day. You might pick another 10 logs on another day. Each one of those groups of 10 logs is called a sample. The 10 is the size of the sample. So you see the size for that sample of n equal 10. Don't confuse sample with its size. The sample is a group of objects. In everyday speech, when we say sample, we often mean one item. Like when you're in the grocery store and they say, do you want a sample of these sausages? They're only going to give you one little bite. So we tend to think of sample as one. But here we mean sampling, and the sample consists of so many objects. And the number of objects is the size of the sample. So you keep taking sample after sample after sample till you have this whole collection of samples. Each one of these samples you average. So you get a mean from each sample. So if you have a collection of 1,000 samples, then you'll have 1,000 means. If you graph those means, you will get something like this. For example, here is a value 4. This would be the value of the mean, the value of the average of the samples, and the height of the bar is the relative frequency, or, depending on how you do it, the number of samples that had this mean. This takes a little getting used to. Okay, so the averages are on the x-axis. The frequency or relative frequency is plotted on the y-axis. For example, here I think this is a collection of 100 samples. Perhaps, say, 55 had the mean of 3. Alright, and maybe only 10 had the mean of 2, and it looks like about 1 had a mean of 1.5. Over here for 5, maybe 1 had a mean of 5. So this is the frequency on the y-axis, the averages on the x-axis, and this is from a collection of samples. Now the first thing the central limit theorem says is that if you keep taking sample after sample after sample, so instead of 1,000, then you have 10,000, you have 100,000, and you keep plotting these histograms, eventually those histograms are going to look like a bell-shaped curve. This is true no matter what the original distribution looks like for the population. So again, to reiterate this, because until you see this, you'll always be confused. The central limit theorem has to do with the averages from a collection of samples. Each sample has so many subjects in it or objects in it, and that's called the size. The number of them in there is the size. For each one of these samples, you take an average or a mean. You plot that. You put the mean along the x-axis, and you put the frequency on the y-axis. And if you have enough, whatever enough is, of samples, that histogram is going to start to look like a bell-shaped curve. Here is a curve of a histogram taken from the lecture notes. In this case, the idea was that you had an assembly line making CDs, and you're in charge of quality control, so every hour or so you pull 25 CDs off the assembly line and you measure them. You measure the radius, and you see, you know, how big these CDs are. Then you would take your sample of 25, you would average all the measurements you got, and that would be one data point along here. Okay, so it says right here 25 CDs, and these are the averages. Now here is a relative frequency for these samples. Okay, the relative frequency of the averages. And you see it's pretty close to a bell-shaped curve. I can't remember how many I had here. I think it was 700 or so measurements. And now you see that histogram is very close to a bell-shaped curve. So that's the first thing that the central limit theorem says. That histogram is going to look like a bell-shaped curve. What's on the x-axis is the averages. What's on the y-axis are the relative frequencies. The next thing that the central limit theorem says is that if you took the average of the averages, that would be right down the mean of this bell-shaped curve, which is right in the middle of it. That mean is exactly the mean or the average for the entire population of CDs. That would mean for this particular factory, the average for all CDs made from this factory is 64.4. That, of course, is a stupendous result. The only way you could make some sort of sense of it is, say, if you took sample after sample after sample after sample until you had an infinite number of samples, you would have measured every single CD that was ever made, and of course that average would be the average for the population. But we don't have to go that far. Once we have this bell-shaped curve, the mean, that would be right down the center of the bell-shaped curve, I kind of missed it there, is going to be the average for the population, and that's why it is called mu. Okay, so we use mu, which is the mean for a population, and that's why that notation is there. Okay. Okay, there's another result. See the standard deviation here? This is called, I should have put for the sample here. Actually, this is not really called a sample, it's called a distribution now. But the standard deviation for the distribution, which is also called the standard error sometimes, that's at sigma. It's related to the standard distribution for the entire population, like this, assuming that's bell-shaped. The standard distribution, the standard deviation for the distribution equals the standard deviation for the entire population divided by the square root of n, and n is the sample size. That means how many objects you're measuring in each sampling. So there's a relationship between the mean on this distribution curve, it's called a distribution curve, and that's that the mean here is the same as the mean for the population. The standard distribution, the standard deviation here is the same as the standard deviation of the population divided by the square root of the sample size. Now, if you remember on the previous slide, if you only have a few samples, this histogram might look roughly like a bell-shaped curve, or, you know, maybe not even so much like a bell-shaped curve. But as you keep taking sample after sample and graphing these relative frequencies of the averages, then you will eventually approach the bell-shaped curve. So the more samples you take, the more the curve looks bell-shaped. Now, the bigger the sample, that means n is getting bigger and bigger, the more the standard deviation starts to shrink. And I'll show that on the next slide. So in this case, we started off with a sample size of 25. Then we increased to a sample size of 50. Then we end up with a sample size of 100. Here's the equation again. Sigma for the distribution equals sigma for the population divided by the square root of n. Well, as n gets bigger, this entire fraction gets smaller. You can see that here. As n gets bigger, the standard deviation gets smaller, and when a standard deviation is smaller, the curve is narrower. So you change the number of samples that you take, your histogram looks more bell-shaped. If you increase the number of samples, if you increase the size of the sample, then that bell-shaped curve gets narrower and narrower. The mean doesn't change, but it just gets closer and closer to the mean. And here's a summary. The averages from a collection of samples is used to make what's called the distribution curve. You put the averages on the x-axis, you put the frequencies on the y-axis to make up the distribution curve. And this curve is bell-shaped. The distribution mean, that's the average right in the center of the histogram, that is the average of all the averages. It's also the mean or the average for the entire population. The standard distribution of the distribution curve is related to the standard distribution for the entire population like this. There's a standard distribution for the standard deviation for the distribution, and it equals the sigma for the entire population divided by the square root of the sample size. This standard deviation for the distribution is also called standard error. As the number of samples increases, the curve, that histogram, looks more bell-shaped. As the size of the sample increases, then the curve becomes narrower and the standard error, the standard deviation, becomes smaller. The mean doesn't change though. Okay, at this point you should be able to do the homework. What is the subject of the central limit theorem? That shouldn't have an S on it. And you can describe that it is a collection of samples taking the average of every sample and then graphing those frequencies into a histogram. So what values are displayed on the histogram for the distribution curve? Okay, on the x-axis are the averages, on the y-axis are the frequencies. And what does it say about the general shape? Well, you know that already. It says it's bell-shaped. Write the expressions for the mean of the distribution curve and its standard deviation in terms of the mean and standard deviation for the entire population. Well, the mean for the histogram curve, or the distribution curve, I shouldn't say histogram curve, is the mean for the population. There's no difference. And the standard deviation for the distribution, or standard error, is the standard deviation for the whole population divided by the square root of n, which is the sample size. If the size of the sample increases, what happens to the distribution curve? It's going to get real narrow. If the number of samples increases, what happens to the distribution curve? It gets more and more bell-shaped. Then there's one sample problem here too for you to do to create that histogram, to find the mean and find the standard deviation. So we've got a machine cutting 20,000 boards a day. I don't know if that's a good number, but say you grab 30 boards off the machine daily and you go and measure them, because they're supposed to cut it to 60 inches 5-foot length boards. And now here are all the average lengths. There were 3 of your samples, maybe taken from Monday, Tuesday, and Thursday, that had an average length of 56. These are the averages of 36 of the 30 boards. 56, that the average of 58, that happened on 26 days. Average of 60 happened on 147 days. This is only part of the table. The whole table, of course, is in the homework. So you find from that the relative frequency, because there were 3,264 days of averages here. And you get to graph it, find the mean, and I've given you a bell-shaped curve to draw on. So here's the bell-shaped curve. You can see the averages are down here. It's already set up for you. They're the averages. So you're going to go through here and you're going to draw in your histogram. I'll hopefully draw a little bit better than that, maybe with a ruler. Okay. So that's the first part of the homework assignment.